Section 9.3 is a section about this question: when does a series converge? And as we know, a series is going to be an infinite list of numbers that get added up. So with our summation notation, it's the sum from n equals 1 to infinity of this term here. So the question, when does a series converge, is the same thing as when does this thing equal a finite number? All right, so that's the question that we're asking. In section 9.2, we saw a geometric series. Which are series that look like the summation of some constant times x to the n, where again, n goes from 1 to infinity. So geometric series are going to converge as long as x is small. If x is bigger than 1, these numbers are going to get bigger and bigger and bigger. So clearly, when we add together these numbers that are getting bigger and bigger and bigger, we're going to get something that's infinite. However, if x is less than 1, it only has to be a little bit less than 1, the numbers that we're adding together are going to get smaller fast enough that it will actually end up being the case that the whole sum is some finite thing. So we converge when x is less than 1. And what we really mean is x is smaller than 1. When x is negative, we want it to be the case that in magnitude, x is less than 1. All right, so this hopefully is something that you discussed in your group last time. In section 9.3, we're asking, all right, well, how else could we determine if a series converges or not? And in section 3, what we're going to be doing are taking these things called partial sums. So the idea behind partial sums is, well, if we want to know if this infinite list of things added together is a finite number or an infinite number, we can start off by looking at the sequence that's formed by taking just finite pieces of this infinite series. And there's a lot of sequences and series and infinites and finites floating around there. So let's take a look at an example. So for a partial sum, I might want to know, or my question is, does the series, so adding together 1 over 2 to the n, going from n equals 1 to infinity, does this thing converge? And so if you're paying attention, you might say that, oh, hey, this series is geometric, and be able to use this statement that we just made up here to answer this. I'm going to pretend that we're not noticing that piece, and we're going to answer this using a partial sums approach. So to answer if whether or not this approach is, what we're going to be doing is we're going to be constructing a sequence. So starting off with our first term, S1, our first term is the sum going all the way to the term 1. So this is going to be the sum from n equals 1 to 1 of 1 over 2 to the n. Well, this is just 1 over 2. And then we're going to say, all right, the second term in our sequence is the sum from n equals 1 to 2 of 1 over 2 to the n. Well, this thing is 1/2 plus 1/4. S3 is going to be uh, 1/2 plus 1/4 plus 1/8, and we can start to see the pattern that's developing. I also want to point out that 1/2 is, well, 1/2. 1/2 plus 1/4 is 3/4, and here we're going to have 7/8. Need a little more, more space here. Okay. So I can go ahead and also put that S4 ends up being 1/2 plus 1/4 plus 1/8 plus 1/16. And this thing ends up being 15/16. Okay, so we've got multiple things floating around here. We've got sequences and we've got series. Our main question is, does the infinite sum 1/2 plus 1/4 plus 1/8 plus 1/16, etc., is this thing a finite number? All right, so that's the series that we're talking about. To answer this, we're looking at a new sequence that we're coming up with, which is going to be taking this a piece at a time. So the sequence that we're coming up with is going to be the list of numbers 1/2, 3/4, 7/8, 15/16, etc. So the question of does this series converge ends up being the same as does the sequence of partial sums converge? In other words, does this number limit towards some specific value? And just by looking at this pattern, we might be able to realize that, hey, the next term is going to be 31/32, and then ends up being 63/64. As it turns out, this thing limits towards one, which is a way of figuring out that, hey, this whole sum ends up actually equaling 1. Okay, I wanted to also include a geometric way of seeing this, sort of a graphical way. All right, so what we're doing is we're adding up, so let's say we've got a square, bigger square. Oh, actually I can insert a square. Cool. All right, so we have our square, and what we're doing is we're going to be adding up. So if the square has side lengths of 1, the total area of the square is 1. So what we're doing is we're adding up 1/2 plus 1/4 plus 1/8 plus 1/16. So let's do that pictorially. Let's say we want to add up 1/2. So we're going to start with this half, and we're going to add a 1/4, and then we're going to add a 1/16, and then a 32nd, and then a 64th. I may have gotten a little bit off. I think I skipped an 1/8, but you get the picture. That each time we're going to be including, so if this is the 64th term, this is 1/64 of the total square. If we're adding up all of the shaded regions, we can see that if we stop at any points, we might have 63/64. But if we keep going to infinity, we're going to get closer and closer to this point. And in the limits, this whole thing is going to, the area of the shaded region is going to end up equaling 1. So this is a pictorial way of seeing why this sequence adds up to 1. I certainly encourage you to take a look at the book. They do a different example, but have another type of pictorial way of seeing how these partial sum sequences can represent what the series is talking about.